So we want to know where the particle is after 2 seconds in this scenario. Well, notice we have an equation here, and we're told that this equation represents the position of the particle. So S means position here. So if I want to know what the position is after 2 seconds, in other words, where it is, I'm going to plug that 2 in for t, wherever t appears. And then it's just a matter of going ahead and doing the math. And so I went ahead and called it S of t in order to keep the notation handy there. And when we work it through and plug in the 2 cubed, of course, is 8. And then when you do 8 times 2 squared, remember, do the exponent first. So 2 squared is 4, 4 times 8 is the 32. And of course, then the 5 times 2. Then we go ahead and do the addition and subtraction. You should get an answer then of negative 14 feet. Now notice the answer is negative 14 feet. So what does that tell us about the location of this particle?
It went backwards.
Yeah. We could say that it went backwards, right? But what does backwards mean? Well, at some point, when somebody set up this equation, they defined this direction is positive and that direction is negative. And they're opposite of each other. Now, we don't even necessarily know what that is. This particle could be sitting in the middle of a floor, and it could be moving away from us. And that's what positive means. It could be hanging on a string, moving up and down. And positive could represent up. We don't know that detail, but we don't need to know. What we do know is that whichever direction is considered negative, it moved 14 feet in that direction, basically, is what that tells us. All right, now, this was all asking about position. Now, position has some very detailed stuff about it, and that's going to be the focus of today, is looking at these sorts of things. So we're going to have some notes along the way. The first set of notes here is about position, and what we really mean by position. Now, some of the details here might seem somewhat obvious, but we're really being detailed here because we're going to see some differences and some information about this going forward here. Like that stuff in italic blue there in the middle. Note that this is different than distance traveled. We're going to look at distance traveled later today, and we're going to see how and why it's different, but how it's also related, and we can use it to find it. But positive position, of course, that moves it, just means it's moved in the positive direction. And it's talking about where it's located in the positive direction. Not like what route it took to get there, but just where it is at that moment. Now, this idea of position is related to velocity. Now, we've done these types of problems before. Given position, find the velocity. Well, remember what we do to position in order to find velocity? Yep, find the derivative. So, take a moment, find the derivative, please, of that equation. All right, so when we find our derivative, we should be looking at this. 3t squared minus 16t plus 5. Because, of course, the derivative of position tells us velocity. Okay, so now that I have the equation for it in terms of t, well, we can now use that as well. So next up, really quickly, please, what is the velocity after 2 seconds? And so once again, we're taking the 2, it's 2 seconds, so we're plugging that in for t in our original equation there for v. So we're plugging it into the velocity. When we do that, we end up with a negative 15 feet per second. Notice our units and how they change. It went from feet, we did the derivative with respect to time, and therefore it's per second now, so feet per second. Now what does this tell us about our particle after 2 seconds? Now, sometimes people get mixed up about what this really means. It doesn't mean that it's slowing down, for instance. A negative 15 feet per second means that it is moving at 15 feet per second in the negative direction. All right? When is this particle now at rest? In other words, when is it not moving? So, if it's not moving, what do we know about the velocity? that it's 0. Yep. So plug 0 in for v and solve your equation from there. Now notice in order to solve this, we're solving a quadratic. While you can use quadratic formula, try factoring it first. It's a much better method because quadratic formula takes so much longer. So we factor it down by your preferred method of choice, whichever you like the most. And then we can go ahead and solve it. Remember, solving it just means setting each of the parentheses equal to 0. And so we end up with 1/3 and 5. So notice those are what t equals. T is measured in seconds, so it's 1/3 of a second and 5 seconds, where it's at rest. Now this is going to be useful information because really we've been building up using some practice of some familiar ideas in order to be able to use it a little bit more. And the first thing we're going to try to figure out with this today is when is this particle moving in the positive direction? And when is it moving in the negative direction? How would we describe that? Well, notice I started by asking when it's at rest. That can be useful information for us on this. And to help visualize what's going on, I'm going to sketch a graph here. Now, you can do this as well when you're facing one of these problems, but you don't have to. As we'll see, there's different methods. But if I know it's at rest, here at 1/3 and here at 5, I know it's crossing through those. If I want to know when velocity is positive, I'm basically saying, is it doing like one of these kinds of things? Is it doing one of those? Or is it doing something else really wonky in between and doing something like this or what? So we just have to figure out what is it actually doing? How's it behaving along the way? So think about the graph of this. What is the shape of that graph going to be? Yep, we know it's a parabola. And this parabola here, it's a positive 3. Therefore, our parabola is going to be opening upward. And so, without even having to figure out the rest of the numbers involved, I can know that graphing it, it's going to look like that. So, can you tell where it's positive or negative? Yeah, because we can just look at this. Now, I can see that basically I've divided my graph up into 3 pieces. To the left of 1/3, is velocity positive or negative?
Negative.
Velocity is positive.
But it's moving
Because, of course, this graph is a graph of velocity. So wherever it's above the axis, that's velocity being positive. Now, how would I write that? How would I say everything to the left of 1/3?
negative.
I was totally going to say that. But I had my hand up like a shell.
Exactly. I just think I'm not sure.
We can write it as an interval, right? And so, I can now go through and I can see where it's positive and negative. And I can describe it by all these intervals. But do you really want to have to make a graph every single time? Probably not. So, without having to make a graph, we still could do this. What we would do is we would plug a value from each interval into the velocity function to test it. So if we didn't want to have to make the graph, we could actually test a point. So for instance, what is a nice, easy number in this interval?
1/3.
1.
I can't use 1/3 because it doesn't include 1/3.
0.
2/3 is too much. It has to be less than 1/3. And I want it to be something easy to plug in the equation. So yeah, let's use 0. Now you could also use -1 or -2 or -3, anything like that. But 0 is super easy. V of 0 equals 5. That was fast and easy. I like that.
Micro USB.
Okay. We got to do the same thing here for our middle interval. What would be a nice, easy number to pick from this interval?
1.
I like 1, but you could also use 2, 3, or 4. Any of those would be pretty easy to plug in, see what they equal. V of 1 here would end up being a negative.
It's 8.
So we got -8 for V of 1. So you see, over that interval, the velocity is negative. And of course you could test the same thing here for this last interval. What's a nice number to pick from that one?
10, 100.
10.
Good. I'm glad none of you said 5. That was the thing that I was really looking for there. It just has to be any number bigger than 5. You could do 6, you could do 10, you could do 100. It could be anything like that. Do we get a positive or a negative number? Should get a positive when you do it. I'm not actually going to plug it in because you know how to do it from there. Now, in the end, whether you do this by graphing or by plugging in individual numbers and testing them, we know that we have a positive velocity between negative infinity and 1/3 and between 5 and infinity. Now, if I just asked over what interval is the velocity positive, remember you'd actually have to write it with the union in there. So you go negative infinity to 1/3, union 5 to infinity. So if we were just asked where is the velocity positive, that's the sort of thing that we're going to be doing. Now, I showed you a couple different ways. If you graph it, you can see visually what's going on there. But when you're testing it, some of you might be thinking, well, let's make our lives a little bit easier. If I know this first one is positive, can't I just assume that it then goes negative positive? Can we just assume what the next interval will be? Will it always alternate like that? Well, again, picture what a graph could look like on this. So bringing you back and reminding you of this. In this case, it did this. So yes, it was alternating. But remember that it could also do something like this, where it goes down, hits it, and bounces back up again. This would be a case where it was positive, positive, negative. And so you actually have to test each interval, check each one individually. Now that we've talked through velocity, we need the velocity notes. So please add this now to your notes following the work you did on position earlier. So the last problem we're taking a look at today is what is the total distance traveled? Now we can't just say total distance traveled, period. Because this goes on into infinity and things like that. So we can't really describe what's the total distance. So we got to define an interval. So we're going to say the first 8 seconds. So in other words, from 0 seconds up to 8 seconds, how far did it travel during that time? Now, if you're thinking find a derivative, second derivative, third derivative, something like that, nope, that's not going to help us here. We need to use a little bit more here. Now, what we're looking for here is we're looking to see how far does this graph go. Now, I can't just say between the start and the end, what's the difference between them? Because if we just went between those, notice that would make it look like we just went like this. But we didn't travel directly from that first point out to that last point.
I get it.
We took a longer route there. We started.
Oh, I did this in physics. Crazy.
We started by going forward.
I did this in food nutrition.
And then we went backwards. And then we went forwards again. We got to count for each of those. So, we need to figure out how do we divide this up then? Well, really what I need to know is how far forward did we go, which looks like it ends right about there. And then we started going backwards. So from that point over to here, we were then traveling backwards. And then we started traveling forwards again. So we need to figure out how far was each of those 3 distances that we traveled. Well, question, what is this t value? Or x value, basically.
1/3.
We know it exactly. Yep. It's the 1/3. Because, notice it's at rest there. That's the point where it was moving forward. It stopped moving, and then it started moving in the negative direction. And so, where's the other one at?
5.
It's at 5. And so, what we need to do is we need to now figure out what is the value at the position specifically at 1/3, and we need to know the position at 5 to see how far down it went. But if we just stopped there, that wouldn't quite be enough information because notice we also have to go to the end point. So we have to go from the first point and to the last point. And so we're going to also figure out what is S of 0 and S of 8, our two endpoints. Because each of those are our start point, our end point, and then the point where it is at rest. So we plug in those values. I'll save you from the computations here. When we plug those in, S of 0 equals 0. So it starts at 0. That's convenient, right? At 1/3, it's about 0.81. That is rounded. At 5, if I plug 5 in for t, because I'm getting each of these by just plugging that number in for t, we get negative 50. And then finally, S of 8, when I plug 8 in, I get 40. That is enough information now to figure out what is the total distance traveled over each of those intervals. So between 0 and 1/3, how far did this particle move?
0.81.
Yeah, that's just 0.81, right? Because we went from 0 to 0.81. Okay. What about over this interval? Between 1/3 and 5.
50.81.
Yeah, notice that would be 50.81. Now, whether you say it's plus or minus here isn't going to matter because we'll have to turn them into positives at the end. But basically what we're doing is we are subtracting our two distances. So it's like 0.81 minus the negative 50. And so then how far is it from 5 to 8? So I'm saying how far is it from negative 50 up to 40? That would be 90. And so each of those intervals then, we can see how far it traveled to go there. Now, the fact that this was positive direction, this was moving in the negative direction, and this was moving in the positive direction, doesn't change that. We're just looking at how far did it travel between those turning points when we change direction. And so then, the last thing we need to do is figure out what is the total distance traveled. Just add them up. All you got to do. And so if I add those three distances all together, I get 141.62 feet. And that's the total distance traveled by this particle. Notice that is not the same, again, if I just took the start point and the end point. Because it started at 0, it ended up at 40. But it went way more than 40 because of the back and forth that it was doing. Now, this is a bit of a process, so you need some notes on it. Please add this into your notes. This is your last notes for the day.